Hello, sir. Myself T. Kaushik Reddy of CACP, and my roll number is 229518050, and my AAT Tech Talk for DMS nothing but discrete mathematical structures is stationary graph and spectral estimation. So, what is the spectral representation of stationary time series? So, stationary time series satisfy the properties. So, the following properties uh, are the conditions or the properties where the stationary time series satisfied. So, first one is the constant mean E of xt is equal to mu, and the second one is the constant variance of xt is equal to sigma square. And the correlations between the observations xt comma xt plus h dependent only on the distance h. This properties ensures the periodic nature of a stationary time series. So the below one is the graph of the uh, properties that ensures the periodic nature of a stationary time series. Next, recall. This is a recall. You can say xt is equal to sigma from I is equal to range from I is equal to 1 to k. Then xi cos gamma it plus yi sin gamma it is a stationary time series. Next, where lambda 1, lambda 2, and lambda k are k values in 0, comma y. Sorry, the bound is not gamma, it's lambda. And capital X1, capital X2, and so on till capital XK, and a capital Y1, capital Y2, and so on till capital YK are independent. Independent random variables with E of xi is equal to E of yi by I is equal to 0. And E of xi square is equal to E of yi square is equal to sigma I square. So with this time series, E of xt is equal to 0, we can give it a non-zero mean mu by adding mu to the equation. Sigma h. Sigma I is equal to 1 to k. Sigma I square cos gamma I h. Next, P rho of h is equal to sigma, or you can say P of h is equal to sigma h by sigma 0 is equal to sigma I is equal to 1 or summation I is equal to 1 k wi cos lambda I h. Next, where wi is equal to sigma I square by summation or the summation of j is equal to 1 to k sigma square j. So the Riemann integral a to b g of x dx is equal to limit delta x is equal to 0 from range summation of I is equal to 0 to 1 g of ci into xi minus xi minus 1. Next, the Riemann Stieltjes integral a to b g of x df of x limit delta x tends to 0 summation of I is equal to 0 to n g of ci into f of xi minus f of xi minus 1 xi minus 1. If f is continuous with derivative f, then integral a to b g of x df of x is equal to integral a to b g of x f of x dx. If f is a step function with jumps pi at xi, then integral a to b g of x df of x is equal to summation of pi j into xi. First, we are going to develop the concept of integration with respect to the stochastic process. Let u of lambda is to lambda is colon lambda tends to 0 to pi, denote a stochastic process with mean 0 and independent increments. That is E of mu of lambda 2 minus u of lambda 1, u of lambda 4 minus u of lambda 3 is equal to 0. So for for the condition of 0 less than or equal to lambda 1 less than lambda 2 less than or equal to lambda 3 less than lambda 4 less than or equal to pi, and E of u of lambda is equal to 0 for 0 less than or equal to lambda less than or equal to pi. In addition, let g of lambda is equal to E of u square into lambda for g less than or equal to lambda less than or equal to pi, and assume g of 0 is equal to 0. It is easy to show that g of lambda is monotonically non-decreasing. That is g of lambda 1 less than or equal to g of lambda 2 for lambda 1 less than lambda 2. Next, it is easy. Now let us define Let us define g of integral 0 to pi g of lambda into du of lambda analogous to the Riemann Stieltjes integral. Integral 0 to pi g of lambda df of lambda. Let 0 is equal to lambda naught less than lambda 1 less than lambda 2 less than so on less than lambda n is equal to pi. Be partition of the interval. Let delta n is equal to max lambda I minus lambda I minus 1. Let lambda I denote any value in the interval. Lambda I minus 1, comma lambda I. Consider Vn is equal to lambda I is equal to 1 to n g of lambda I into u of lambda I minus u of lambda I minus 1. Next, suppose that limit n tends to infinity, delta n is equal to 0. And there exists a random variable with such v such that limit n tends to infinity e into vn minus v whole square is actually whole square is equal to 0. Then v is denoted by integral 0 to pi g of lambda du of lambda. Properties. So first property is e into integral 0 to pi g of lambda du of lambda equal to 0. Next, second one is e into integral 0 to pi g of lambda du of lambda whole square is equal to integral 0 to pi g square lambda dg of x. Sorry, lambda. Next, third one, e of 0 to pi integral 0 to pi g1 of lambda du of lambda into 0 to pi integral g2 of lambda du of lambda. Then the final, after multiplying the final answer we get, or the final property we get is this is 0 integral 0 to pi g1 of lambda g2 of lambda dg of lambda. Next, let x of lambda colon lambda tends to 0 to pi, or the condition or the range is lambda range is 0 to pi, and y of lambda is 1 and the range is 0 to pi. Denote an uncorrelated stochastic process with mean 0 and independent increments. Also let f lambda is equal to e of x square lambda is equal to e of y square lambda. For 0 less than lambda less than or equal to pi and f of 0 is equal to 0. Now define the time series x1 is to t in the range of t as follows. Xt is equal to integral 0 to pi cos lambda t into dx of lambda plus 0 to pi sine lambda t dy of lambda. Then e of xt is equal to e of t into integral 0 to pi cos lambda t dx lambda plus 0 to pi sine lambda t dy lambda is equal to e into integral 0 to pi cos lambda t dx of lambda plus e of integral 0 to pi is sine lambda t dy of lambda. After adding, we'll get the final answer is 0. Also, sigma h is equal to e of x t plus h into xt is equal to 0. It's equal to e of integral 0 to pi cos into lambda into t plus h dx lambda plus integral 0 to pi sine lambda t plus h dy lambda into integral 0 to pi cos lambda t dx into lambda plus integral 0 to pi sine lambda t dy of lambda. Next, we'll get the after multiplying we get e into 0 to pi cos lambda into t plus h dx lambda into 0 to pi cos lambda t into dx lambda plus e into integral 0 to pi sine lambda into t plus h dy lambda into integral 0 to pi sine lambda t dy into lambda plus e into integral 0 to pi cos lambda t plus h dx lambda into integral 0 to pi sine lambda t dy lambda plus e into 0 to pi sine lambda t plus h dy into lambda into integral 0 to pi cos lambda t dx into lambda. Next is equal to integral 0 to pi cos lambda into t plus h into cos lambda t df of lambda plus integral 0 to pi sine lambda into t plus h sine lambda t df into lambda plus 0 is equal to integral 0 to pi cos lambda t plus h or sorry, cos lambda into t plus h, sorry, cos into lambda into t plus h, cos lambda t plus sin lambda into t plus h, sin lambda t df lambda. The final we get is integral 0 to pi cos lambda h df lambda. Thus, the time series xt defined as follows: xt is equal to integral 0 to pi cos lambda lambda t dx of lambda plus sine integral 0 to pi sine lambda t dy lambda is a stationary time series with mu is equal to e of xt is equal to 0 and sigma h is equal to integral 0 to pi cos lambda h into df of lambda, where f of lambda is called the spectral distribution function. If f of lambda is equal to capital F dash of lambda is called spectral density function. Next, sigma h is equal to integral 0 to pi cos h lambda h df of lambda is equal to 0 to integral 0 to pi cos lambda h f of lambda d lambda. Note, where xt is equal to sigma of 0 is equal to sigma 0 to pi df of lambda is equal to integral 0 to pi f of lambda d lambda. The spectral distribution function f of lambda and the spectral density function f of lambda describe how the variance of xt is distributed over the frequencies in the interval 0 to pi. Next, the autocovariance function sigma h can be computed from the spectral density function f of lambda as follows. Sigma of h is equal to 0 integral 0 to pi cos lambda h f of lambda d lambda is equal to integral 0 to pi e power I lambda h into f of lambda d lambda. E of I theta is equal to cos theta plus I sin theta. Also, the spectral density function f of lambda can be computed from the autocovariance function sigma h as follows. F of lambda is equal to 1 by 2 pi into sigma of 0 plus 1 by pi summation of h is equal to 1 to infinity sigma of h cos lambda h. So this is an example for the above topic. That is IB identity distributed and uncorrelated with mean 0, a white noise series. Thus, sigma h is equal to sigma square h is equal to 0 and 0, so h is not equal to 0. And f of lambda is equal to 1 by 2 pi into sigma into 0 plus 1 by pi into sigma h is equal to 1 to infinity sigma h cos lambda h. Sigma square by 2 pi if minus pi less than or equal to lambda less than or equal to pi. So this is the graph where on the left side is minus pi. We know that the numbers before the y-axis is negative and after the y-axis are positive. So minus pi to pi interval and the frequency is lambda. Next example is another example for the same x1, x1 and xn, y1, y1 are the independent random variables. Then the final answer we get is sigma h is equal to sigma summation of I is equal to 1 to k sigma I square cos lambda h. Another important comment in this case, when f of lambda is continuous and f dash of lambda is equal to f of lambda, then sigma h is equal to integral 0 to pi cos lambda h f of lambda d lambda. So the spectral density function of MA series. So these are the graphs. This is an example when q is equal to 2 after substituting the given formula sigma square by 2 pi mod sigma is s is equal to 0 to 2 alpha s e power minus I lambda s whole square mod. After solving, we get the answer as sigma square by 2 pi 1 plus alpha 1 square alpha 2 square plus 2 into alpha 1 plus alpha 1 alpha 2 into cos lambda plus 2 alpha 2 cos 2 lambda. So next, the spectral density function for MA. These are the graphs when alpha is equal to minus 8 of spectral density function, and alpha 1 is equal to 0.710 and alpha 2 is equal to 0.20. So yeah, thank you. This is my 8 Techtalk for DMS, discrete mathematical structures. Yeah, thank you.